Hello.
How are you?
How are you? Good.
Cool.
Um, okay, so I
That stuff.
was going over functional groups. I found another site.
Is that like medication?
Huh?
Medication
What's up?
on your face?
Yeah, sorry, I have like cream on.
Yep.
Okay. I'm just starting to get ready from now so that I can go longer later on. Um, yeah, so I was
Wait, what?
looking at because I have Shabbos dinner, so I got ready from now.
Mm-hmm.
Or started to, so that I can have more time for a lesson today.
Uh-huh. Got it.
Yeah, I keep opening this one. Yeah. So, okay, so there's like tiny bit of these left.
Hmm.
We finished this one. I think this one and the next one I flagged and I didn't answer because I wanted us to go over them together. I have no idea.
Sure. Which of the following statements is true regarding the hydrolysis of carboxylic acid derivatives? Okay. What are your thoughts here?
Would you draw them out
So
or
like
think
for
about like
uh-huh.
um we talked yesterday about how like things that are electronegative are worse leaving groups, so that it would probably be harder to hydrolyze, which hydrolysis is,
So this is talking about carboxylic acid derivatives.
yeah.
So what can you tell me about those?
Um, well, they're saying like amides, esters,
Yeah, so what are those?
functional groups.
Yeah. What? Like, describe them. Like, what do they look like?
What do they look like? Okay, so amides have the amine, right? So there's a nitrogen at the end, and then esters are
So
the
what is an amide?
it has the N at the end of it.
At the end of what?
Like when you're drawing it out, there's like an N at the on the last carbon.
Yeah, but that doesn't tell me anything. What are you drawing out?
The functional
Well,
okay.
it's a functional group, but I'm saying, what does it look like? Hmm?
Right? That's amide.
Yep. It'll probably have like some H's there.
Okay, yeah.
Good. Okay. What about an ester?
An ester is same this, but shoot, I can't remember. R was ketone. Was it the no? Was it OH? I'm like really struggling to memorize these
Mm-hmm.
for all the prep that I've put into it.
Yeah. So,
I
um,
literally spent like 2 hours going over flashcards for them yesterday
uh-huh.
and today again. And the second I'm not like it's not in front of me, I don't know it.
So, okay. So let's think of what it could be.
I remember R was the ketone.
Okay.
There was one that had an O at the end of it, like here was an O,
Just to know.
OH.
All right. What's that?
I always say hydroxyl and you say
I
that it's
know. But I mean, so you're saying something with like this.
yeah.
So what is that?
I I don't remember what it's called. Like we were talking about amides, ketones, esters,
Okay.
and there was one more that you drew.
And all of these are what derivatives?
Carboxylic acid derivatives.
And what is a carboxylic acid?
This.
So that can't be an ester then, right?
Just with the double bonded. Oh no. This.
All right.
Oh, with the
That's
OH to carboxylic acid, right.
Like what you want to know when you see this, right? Instead of just memorizing it, is what does it do? Well, it would donate protons,
Right.
right? So this will just be O minus plus H plus, right?
Uh-huh.
And why is it doing that? Well, this can go here, that can go there to give you this. So there's resonance stabilization when it loses a proton, which is why it's an acid, right? An acid wants to donate protons, so it's going to be more stable after it's donated its proton.
Mm-hmm.
And you could see that it gets more stable because once it donates its proton, there's resonance stabilization, right?
Yeah.
So if you remember this, then you won't forget it.
For carboxylic acid specifically.
Uh-huh. Yeah, like in general, resonance will just make something more stable.
Mm-hmm.
So in an amide, for instance, there's a lone pair on the nitrogen, which means that this can go here, this can go there. And so this molecule would be O minus and then double bonded to the NH2. So we see that amides also have resonance stabilization, right?
Mm-hmm.
So, that's another way of, that's some more information about uh, amides and carboxylic acids.
So the OH gets broken into the um acid and a hydrogen
Wait. Say, what? Say that again?
for carboxylic acid.
Uh-huh. So which one is the acid?
This.
Um,
Or well this is
what does an acid do?
proton donor.
So is this donating proton?
No, this is the one that donates the proton.
All right. So this is the acid, right? We could say
Right.
HA.
Yes.
And then what would this be?
Is this the ester?
Uh, well, okay. Um, so let's just talk about an acid, H and A, and this breaks apart into H plus A minus.
Mm-hmm.
So this is the acid, and this is called the conjugate base.
Yes.
So once an acid loses a proton, it will be called a conjugate base, and it'll be that negatively charged molecule.
Right. So this is the conjugate base, but doesn't
Yeah.
this have a name as well?
Its name is going to be, so if we start off with carboxylic acid, this would be
A.
carboxylate. Yeah.
Yes.
So that's that. Now, an ester is when you have an OR group here.
But I thought the R was ketone.
Well, that's the R though.
Oh, so when it's an OR, it's okay.
Mhm.
Right.
What if
Yeah.
it was an H?
Next to the R.
If you got rid of the R and it's just an H?
Isn't that a No,
Oh, what?
a hydroxyl.
So, all right, what is a
Every time
hydroxyl?
I see, I know what a hydroxyl is. It's an O
What
and an
is
H. I don't know why I keep doing that.
so if we had an H here, how would that be a hydroxyl?
It wouldn't because of the carbons. Um,
Mhm. So this is an aldehyde.
okay. So H is aldehyde, R is ketone,
Mhm.
OR is ester.
Mhm.
What am I missing?
And then if it's NH or an amine attached to the
NH2
carbon,
is amine.
no, so
Amide.
yep. And it doesn't have to be NH2, it could be like NHR,
4.
but
Okay. All right. So
there's also this, which is an acyl chloride.
that one I remember.
And then there's this, which would be an anhydride.
Okay.
So now let's try to figure out the stability of anhydrides, acyl chlorides, amides, and esters, like relative to one another.
Okay. Well, we know that carboxylic acid is well, they're talking about resonance. So this one is
So
like
just without even looking at that, so just consider amides, esters, acyl chlorides, anhydrides. And then tell me like the relative stability of them, or like list them in order of like
stability.
decreasing. Yeah, maybe like in order of like uh
Wouldn't an
decrease.
anhydride be the most stable
Um so
because of the structure is, but I guess it doesn't have a charge. None of them. Or
so what did we talk about that can give something stability?
well, like for amides, like for example, the negative charge can go and then this can become a double bond
So what is that called?
resonant.
Okay. And what does resonance do to molecule?
It makes them like stable, like it's
Yep.
energetically favorable, like no
So they're more
charge.
stable, right?
Yeah.
So would anhydrides be more stable?
No, amides would be
Good. So amides would be the most stable. Um, what next?
this one.
So
Acetyl chloride.
what is this chlorine doing? Like what is that chlorine doing to the molecule?
Well, chlorine has a negative charge. It's electronegative.
So what does that do then?
And that would make it harder to break down. But also it would be a partial negative, and that would give oxygen a partial positive. Or I think.
So, okay. So the chloride, the chlorine part is electronegative, so it pulls electrons towards itself, right?
Yeah,
So
which would
where's
mean that oxygen would have a partial positive.
where's the chloride attached to?
The carbon.
Okay. So
So there would be like a negative charge that leaves, and this would become a double bond.
no. So think about in terms of, so if chlorine is electronegative, it's pulling electron density from what?
But oxygen is also electronegative, so
Yeah,
can't be from the oxygen.
exactly.
So
So
it has to be from like the hydrogens around it.
I mean, what like what else is there though? But like,
There's carbons.
yep.
I said
So
carbons, you really said no, what else is there?
no, you said oxygen,
No, I said
then you
carbon. Okay,
said
whatever. It doesn't matter.
hydrogen, but you're just kind of like saying random stuff. So
I know.
uh but so first of all, like we go back to base. So let's just have a regular carbonyl group here. Now, what can you tell me about this?
Okay, here oxygen has a negative charge. So that
Well,
means that the carbon, so partial negative, carbon has a partial positive,
okay,
and resonance, it'll lower.
so right now there's no resonance, but you see that the electronegative oxygen pulls electron density towards itself,
Hmm.
giving it a partial negative charge, and the carbon a partial positive, right?
Hmm.
Now let's say we have a chlorine here, which is also electronegative.
Hmm. So I
So
think that that would also have a partial negative, and it would also take from the carbon.
exactly. So it
But the
makes this
overall thing would have a negative charge, right?
so it makes this carbon have even more of a partial positive charge.
Hmm.
And since we're taking so many electron density, like so much electron density from the carbon, it's not going to like want to exist like that,
Hmm.
right? Because the entire reason why this is a good electrophile, for instance, when we have hydroxyl attack it, is because it has that partial positive charge on the carbon, right?
Hmm.
Like if it didn't, it wouldn't attack it, right?
Right.
So now imagine when we have the chlorine here, the partial positive gets even more positive, which should mean that this would react with it even more so,
Hmm.
right? Because if it like if I had just CO2, right? Would this attack that?
No, because there's no hydrogens for the carbon to link to. Like,
I mean, it doesn't, there's no hydrogens
right, but it can't
there.
have a charge. Like, if you're saying the OH is would attack,
Mhm.
I'm pretty sure the thing with it is that there's the oxygens both have partial negatives and this has a partial positive, so it's overall stabilized and there's no charge for H2O.
Yeah, so you're having it like, in opposite directions in this symmetrical molecule, so it won't attack that because you don't have a net dipole, right? For
Hmm.
instance, you can have like partial positive, partial positive, partial negative, a dipole moment going in this direction, partial negative, a dipole going in that direction, and they cancel out, right?
Right.
Um, but here we have a dipole going up like this, and then we have a dipole
Going
going
to the
that
side.
way, and they're not really going to cancel each other out, but they're both going to contribute to making that carbon, the carbonyl carbon, very, very partially positive,
Positive.
and
Yeah.
therefore more reactive.
Yeah.
And if it's more reactive, it's less stable, right?
Mm-hmm.
So, and that's similar for an ester, right?
Mm-hmm.
Because this one is going this way and this goes this way too, right?
Yeah.
So that'll make the carbonyl carbon be more partially positive. And so an ester could be reactive too. It won't be as reactive as the acyl chloride because chlorine has a higher electronegativity and therefore, creates a more partial positive charge on the carbon. But esters will also do that.
How come? Don't oxygen have, isn't oxygen more electronegative and now there's two of them? Is it
You're,
assuming that the
you're
R group
comparing,
is less reactive?
wait, are you comparing oxygen to what?
And chlorine,
Well, chlorine is more electronegative.
FON, Cl.
The oh, you're saying like in that regard?
Yeah, like we were just went over, it goes up.
Uh-huh. So
Oh,
like the halides are pretty um electronegative.
so, but the order of electronegativity is FONCl, bromine, ISCH.
Okay, we could say that it could
I'm
then
just,
be from the R group then.
okay.
Um, so because yeah, the R group is going to be some like more carbon hydrogen bonds, so we can take electron density from that also. But overall, the order in terms of increasing stability would be so acyl chlorides would be the most reactive, followed by um, anhydrides, followed
Okay.
by esters, and then lastly amides.
Mm-hmm.
So that's the order of stability. So for this one, they're asking what's true if you hydrolyze carboxylic acid derivatives. And so the first part of these say amides, hydrolyzing amides is more difficult than esters, compared to hydrolyzing esters is more difficult than amides.
Mm-hmm.
So since we know that the amide is the most stable carboxylic acid derivative because it has resonance, it would be more difficult to hydrolyze amides, right?
Yes,
Hmm?
because A.
Mm-hmm.
Oh, it doesn't let me click it, but yeah.
But yep. Oh yeah, and then this is just
Reactive, this is the opposite.
mhm.
Um, between esters and anhyd or
Yep. So it'll go in the order of
amides
Yeah, amides would be the most stable, so least reactive.
Then esters,
Mm-hmm.
then
Mm-hmm.
I'm just confused where anhydrides fall in this.
Oh yeah, so they're going to be in between in terms of stability. Anhydrides would be between esters and acid chlorides.
Because the oxygen in all of them.
When you say in all of them?
Well, isn't that what like the three between D, C, and B, what they all have in common is the oxygen. Like for esters, the R group is present, so
So wait, you're saying what's common in all of them is which one?
like the presence of an oxygen in that like group at the bottom. Where
Um,
hydrides has an extra two oxygen.
sorry. So what are you? So you're saying?
Like I'm trying to like
Mhm.
reason out in my head like why acetyl chloride would be last, and I'm saying that like compared to, oh, I guess no, amides, never mind. Amides would be the most stable, and then between like anhydride, acetyl chloride, and ester. Anhydride and ester both have oxygens, and then their like respective R group thingy. Like for ester, it's literally an R group, and for oxygen, it's another one of the carbonyls,
Okay.
which stabilizes it, right? So the presence of that oxygen is what makes it more stable than say the acetyl chloride, which has just the chlorine. Or am I going like too far off and it's
So yeah, so the acid chloride is going to be the most reactive because, well, one, yeah, it'll make that carbonyl carbon more partially positive. And also because it's a good leaving group, the chloride ion, it can leave and just, exist as chloride ion in water.
Mhm.
Yeah.
Okay, so where does the ketone and aldehyde fall on this?
Oh yeah,
Like
so those
aldehyde would be a good leaving group, so it would be even further, like after acetyl chloride, right?
so these are all carboxylic acid derivatives, so they're
Uh-huh.
derived from carboxylic acid.
Right.
So ketones and
Aldehydes
aldehydes will
aren't.
be, yeah.
Okay. Okay. Sorry, I'm just writing that down, but that makes sense. Okay. So the most reactive is acid chloride.
Mhm.
I think I got acetone from the name, but I'm not sure where I got CO2. Propane, we talked about pro is 3, right?
Mhm.
And so when you're looking at these, like, do you visualize it in your head? Like, what does acetoacetic acid look like?
Yeah, I would I would likely draw it.
Uh-huh.
Um,
But what if, like, for me, I don't know what it looks like.
uh-huh. So,
I got 2 from the name,
uh,
but
yeah. So I guess you can think of well, what about maybe acetone?
Right.
Would that be something that maybe it's like?
Acetone, isn't that like a type of alcohol? It's like similar to rubbing alcohol, no? Like
Uh
acetone is the nail polish remover.
so look at you can tell by the last like the suffix what type
Oh,
of
and
molecule it is.
yeah, we learned. You told me about this.
Yeah. So what's the suffix for acetone?
Oh, any.
All right. And that would be uh
Um,
mhm.
I don't remember.
So what other functional group ends in ONE?
Ketone?
Yep.
Oh,
So
so just automatically acetone is a ketone.
wait, what's up?
So that just automatically like acetone is a ketone.
Yep.
Oh, that's easy.
Hmm.
Is that the same with like ides? Or
Uh,
a little bit more complicated because they all end in some.
IDE you're saying?
Well, like, yeah, a lot of them end in
That would be like if you had a
carboxylic
negatively.
acid derivatives end in ID.
Oh no, so that's when you have like an anion of something.
Mm-hmm.
So like chlorine negative would be chloride,
Mm-hmm.
right?
Okay.
Halide, you know, things like that.
Mm-hmm.
Yeah. So acetone looks like this with CH3s on both sides.
Uh-huh.
And acetoacetic acid would mean that we would have to add a carboxylic acid to this. So this is going to look like this.
Mm-hmm.
So,
They just all look so similar.
uh-huh. Yeah. But I mean, there's those, I mean, like, I guess this kind of looks a little bit like an anhydride, but an anhydride would have an oxygen in the middle. Because the thing is, like, yeah, if you just look at the structures, they do look similar, but if you think about how the structures are made, you can then see, for instance, if I had two carboxylic acids like this, and this loses a proton, becomes negative, it can attack this, right? Meaning that when it makes the anhydride like this, like I'll label these like, so let's say this is the green, this is green, that's that one. And let's say this is pink. The nucleophilic oxygen is this guy over here.
Mm-hmm.
And then this breaks away, so that's no longer there. So that's how you get your anhydride. But as far as the like, so I know that this looks similar to this, and I don't
But it's
think
a
that
lot of
they'll.
oxygen in the middle. I just meant like overall the structure, like when you drew out an acetone, like comparing that to like, but I guess if it's a type of ketone,
Yep.
the CH3 is the R group in this case.
Um. Yeah. Yeah. So like you
Okay.
should also know like the that an acetyl group is basically um this, because that comes up a lot with like histone acetylation, you know,
Mm-hmm.
acetyl CoA, right?
Yeah.
Like when pyruvate enters into the Krebs cycle, it well, it's pyruvate's 3 carbons, and acetyl group is 2 carbons, so when pyruvate turns into acetyl CoA, it loses a carbon as CO2.
Mhm.
So yeah, for this, I don't think they'll ask you like, what acetic acid would look like,
Mhm.
but you would have to at least know that it will have a carboxylic acid group in it because they said acid, and that's the organic acid that we typically see.
Mhm.
And then acetone is, basically nail polish remover, and that's just this with the CH3s on both sides.
Right.
And then if you think about um, acetic acid, it would just be this. So you take the existing acetone
Mhm.
and
And you
you,
had that.
yeah, you turn that into a carboxylic acid. So that's that. But yeah. So for the different, like, aldehyde versus ketone versus carboxylic acid versus ester versus blah blah blah. You'd want to see them as like, okay, they all have the carbonyl group. It's just that the thing that's attached to that carbonyl carbon is different, and you want to know what the different ones are.
Okay.
Yeah. So for this one, we're going from this to this, right? We
Mhm.
have 1, 2, 3, 4 carbons in acetoacetic acid, 3 carbons in um acetone, right? Right.
Yeah, yeah, yeah.
And then we have 2 oxygens in acetoacetic acid and 1 oxygen in acetone. So we're losing sorry, I wrote 2, but 3 oxygens to 1. So that means we're losing we're losing 1 carbon and 2 oxygens.
Right.
So so this is could just be CO2, right?
Mhm.
So, and that's what happens in a decarboxylation reaction. You lose a carbon and 2 oxygens in the form of CO2. And
So even without knowing what happens when the reaction is heated, like how it acts, like we know that propane would not be involved in this in any scenario, right?
yeah, because propane would just be like 3 carbons,
Three
right?
carbons.
Mm-hmm.
Okay,
Yep.
sounds good.
Mm-hmm. Yeah. So we saw something similar before when we talked about SN1 and SN2, right?
Mm-hmm.
Yeah.
How if there's
Mm-hmm.
I can't remember what the word was, but like it was like a characteristic of an SN1 reaction because it wouldn't have that like state in an SN2 reaction because it all happens in one like
Yep.
one reactive step. So that would be an SN2 reaction where the ratios remain stable, right?
Yep. Oh, wait, sorry, SN1. Because so SN2 would give you one product with inverted stereochemistry,
Right. Okay.
aka like in an enantiomer. SN1 though would give you both enantiomers in equal amounts, and that's racemic. and it doesn't have any optical properties because they cancel one another out. So this is similar to that type of question, except when they say elevated temperature, they introduce elimination reactions. So we know that SN1 and SN2 are substitution reactions. We're replacing one atom with another. Like we're replacing a leaving group with a nucleophile. But for elimination reactions, we get rid of the leaving group. We don't get to add the nucleophile, but what we do add is a double bond. So
Which
that's,
is the hydrogens being eliminated and creating the double bond.
yeah, so that could be something like that. Yeah.
Okay.
So now if they're saying that if this happened with elevated temperatures, would it shift towards compound 1 or compound 2? And we want
How
it.
do we know that it's compound 1 versus 2? Like
Yeah.
based off of the structure, like this double bond is here, so it's this hydrogen.
Uh-huh. So yeah, if you have your double bond here, it's between these two substituents compared to here where it's
Between
between
oxygen
and then just
carbon.
that carbon there.
Okay.
So this is going to be more stable.
Right, that makes sense.
Mhm.
Okay. I get it. Acetone is treated with one equivalent of methanol. I know we went over it yesterday, but now that I'm like drawing out all these structures for myself, like maybe it's because I'm looking at it on a computer screen that it's not working. Maybe if I draw it out, it'll be easier. Can we do ethanol and methanol one more time and then I try to solve this on my own?
Oh yeah, totally.
Can you just like ethanol is, I know methanol is the one that has one, right?
Uh-huh. So what so are you what are
Like
you
I just
with
I
ethanol?
want to like visualize the structure quickly and then I want to try to solve the like
Sure.
question, like the information that I have.
Yeah. I'm just asking
Acetone.
about the ethanol though.
I know, but
Like yeah. What about
I just like methanol, ethanol, like there's
uh-huh.
I want to like visualize both of them so I can have it and I'm like writing out on a
Yeah,
piece of
yeah, of course. Mhm. Sure. No, I was just asking because I was just asking about the ethanol part. But anyway, go on. You can draw
No,
it.
no, I'm asking like can we draw them out together like now so that I can because now I know what acetone looks like. I want to see if I can solve this problem
Sure.
like given that. So
Yep.
what does methanol look like?
So look at the suffix.
Oh well.
Yeah. So that should indicate to you a functional group. So the OL suffix is for alcohols,
Oh, okay.
which have hydroxyl groups and only hydroxyl groups. So that's exactly like your usual answer, but this time it's right.
This is methanol just
Mhm.
like
Yeah.
what is the structure of alcohol? It's like OH.
So the meth part would mean how many carbons?
One.
Mm-hmm. So
So
yeah, go on.
one carbon OH.
Exactly. Yeah.
I mean, does it matter how you draw it? Like, right? And like for ethanol, it's this.
Yep. And ethanol is basically like the alcohol that we drink.
I remember that from The Big Bang Theory when he ordered ethanol.
Oh yeah.
Okay, all right. Now, acetone is
Mm-hmm.
and then methanol would look like that.
So,
Or do you add them?
mm-hmm.
So you have, I really hate this thing,
Mm-hmm.
treated with, yeah, plus.
Good.
Would it not just come up and end up being like that?
So think back to what I say always about most common blah blah blah.
What is it being more common?
Like you know how I always say something
Yeah,
the most yeah.
and I always say it's the most common, it's hydroxyl is the most common functional group, and you always say something else,
Nucleophile?
nucleophile, which is a proton donor.
Mm,
And carboxylic
it's not a
acid
proton
is
donor.
a most common electrophile.
Uh no. So it's the most so the a nucleophile is Lewis base, which means it's an electron pair donor. But think about the word nucleophile, right? It likes to bond to things that are positive or negative.
Positive.
Okay. So
So nucleophile is a base.
Lewis base.
Yes.
So and then so I also say something is the most common electrophile.
Um, carboxylic acid.
Uh really just something with
Carbon.
the carbonyl group.
Okay. So just the carbonyl is the most common
Yeah.
electrophile.
Like yeah, things with carbonyl groups.
Okay.
So, you know, so like why is it that it's carbonyl groups?
Because is it because that's like the base of all of these different like groups?
So
They're
whenever
less stable, so they can take in
I draw a carbonyl group, what else do I draw?
a hydrogen.
Um, so like when I draw something like this, and I draw something like this, what do I do?
Charge.
Okay, go on.
We have a charge. We draw the partial positive and partial negative.
Yes.
So they're not stable.
So
It's that they're Lewis acids and can donate protons. So they're least
wait, so go back to the partial charge thing.
uh-huh.
So Yeah. Show me where those partial charges should be.
Well, oxygen is partially negative,
Okay.
so you show like music notes.
Mhm.
And then the carbon is partially positive.
All right.
And
So
then if there's like an oxygen or something at the end, the carbon just becomes more partially positive.
so now that nucleophiles would be attracted to the what?
Part positive charge.
Yep.
So it would attack it.
Yep.
Uh-huh.
It'll attack it where?
Here.
Yep. So you could draw an arrow, right?
Mm-hmm.
This would attack that, right?
Right.
Forming a bond with it, right?
Yes, but that carbon has 4 bonds.
So
Which means that something has to be broken.
so it will it'll
Oh, so this can go here. This
exactly.
loses the negative charge. It becomes OH, right? With one
So remember, these are
thing.
partial charges. So here, I'll draw it again here. There's a partial positive here, partial negative, right?
Right, but if it attacks it, doesn't it become more negatively charged or partially positive because it's now another oxygen that's attacking it?
Well, that's other oxygen attacking it is donating an electron pair.
Uh-huh.
So
Mm.
so if it donates an electron pair to something that's partially positive, that should make it less partially positive, right?
Yeah.
So that's why it'll
Yeah.
attack that, right?
Okay.
And
So that
when it
means
attacks that, forming a bond with it, as you said, carbon can only make 4 bonds.
mhm.
So that's when I draw this thing, right? Where I draw like the electrons from this double bond go to the oxygen, right? So you would get that OH bound to this like that.
Mhm.
And it will then reform the double bond. And then let's say this is a leaving group, kick off the leaving group to then give you the OH bound that way, right?
This looks like the dipole thing you drew 2 questions ago.
The dipole thing?
Like just the way that looks.
Mm-hmm.
The
Yeah.
two.
Because what's happening is it's making a bond with the carbonyl carbon and then shifting the electrons from the double bond to the oxygen. So the oxygen now has a full-fledged negative charge, no longer partial, like actually negative.
Mhm.
And it doesn't want to do that. It doesn't want to be like that. Like in general, if you concentrate a charge at a specific region, it's not stable. But if you can spread that charge, it's more stable. So it's
Mhm.
going to come back to reform the double bond, but this time it'll kick off the leaving group. And then you would have your product, which is nucleophile added to that electrophile, minus the leaving group.
Got it.
Mm-hmm. So now back here, right?
So
You
this
know
is
that,
the OH like that's here. We've already added it on,
yeah,
right?
yeah. But you see how we're adding it with by adding the bond to the oxygen.
Mm-hmm.
So this here is it would be the case if this carbon bonded there, but it's the oxygen that should bind there, right?
Yeah.
So yeah.
How does this look like B? Because the R is the extra carbon,
Let's see. So,
like the double bond.
oh, okay. So now this is okay. So what we drew here is what would typically happen in that SN2 reaction, like producing essentially an ester here, right? If you think about it, this is an ester because there's an R group here, right? And an ester is,
OR.
yep. So this is O and this is the R, right?
Mm-hmm.
So that's what'll happen normally, right? But now they're
Mm-hmm.
saying that this is an acidic solution.
So
Mhm.
we supposed to use acetone or acetyl chloride?
Wait, well, it says acetone and
Yeah,
methanols, right?
but when it's in an acidic solution, doesn't that change the structure of it?
Um,
But I guess not the like, what's the one, the acetoacetic acid that we drew that was like oxygen and then an extra thing?
uh-huh. Yeah, if it's you're talking about, yeah, the acetoacetic acid would be
Yeah.
like uh the acetone like portion and then the carboxylic acid portion.
Okay, so that's wrong.
But so okay, so this acidic solution, so that means this step here, right? Um, this is what would happen, to make this in normal solution.
Mm-hmm.
However, if since we have, oh God, that just eliminated. All right, so what did I have? Okay. So here at this step, if we now have this as a and in an acidic solution, this O minus would just take a proton from the acid, giving you that OH there, right? And this OH here, like, we're not worried too much about that as an OH because it's really an OR group, this thing, right? The methanol part.
Mm-hmm.
Like I could just write it as methanol as ROH with R just being, CH3 or whatever.
Mm-hmm.
So so this turns into like OH, OR, and then this, I mean, I called it the leaving group for this example, but if it's acetone, it's CH3 on that side, CH3 on this side, right?
Right.
So
Bottom
it's
straight.
just, yeah, left that way. So this
Okay.
would be just like that. And so it'll be this. And this, by the way, is a Hemiacetal. And this comes into like this is connected to sugars, and if sugars can be reducing sugars or non-reducing sugars, that topic.
Mhm.
So, that'll be something that you'll see probably soon. But
Okay.
yeah, I always stress an interdisciplinary approach. So noticing this as a hemiketal, you'll see will help you once you go into sugar stuff.
Okay. If I got another question like this, how would you approach it?
Okay. So I would first take a look at what,
Acetone and the methanol?
yep. And, you know, I would end up with something like this, right? And I guess, well, I mean, two things. One, if you read that it's in an acidic solution, then you're going to go at it that way. I missed that at first, so I just drew this product. Oops. And so that that's the product. So like, okay, if you have your let's just say if you take a ketone and you make it react with an alcohol, it can turn into an ester. But if you're doing it in an acidic solution, it'll turn into a hemiketal. So, yeah.
So, yeah, I guess this is the part that confuses me, where it's like it went from
Mhm.
this answer to then we added the hydrogen back in, and then this became an R group, which I guess theoretically makes sense. Like I understand how you explained it completely. I'm just confused,
Mhm.
you know.
Yeah.
Then we like lost a carbon here in the R group. The OR became this part.
Oh, yeah. So the carbons stick around. We still have
They
them.
just switch places.
Oh, no. They're still there. Um, yeah. Maybe I
Okay,
can, because we have 1, 2, 3, 4, right?
right.
Let's call it this 1, let's call this 2, let's call this 3, and let's call this 4. So
Mhm.
that's going to be 1, 2, 3, and then that one 4.
But yeah, the four makes sense. Okay,
Yeah.
all right.
So there you go. And then
Okay.
I should also just say that this would be a full-fledged ketal, and you'll see stuff like that in sugars.
And
Sugar
what about
chemistry.
these two?
Those are just, so that one I guess is just some diol of some sort, not really an important thing. And uh, uh then D would just be like a secondary alcohol.
Okay, all right.
Mhm.
I'm gonna run to the bathroom for 2 seconds and
Yep,
then
yep.
okay. I'm like
You can go to like the next one and I'll be able to, or yeah, it doesn't matter.
hey, I'm back.
Okay.
We for sure need to do this. Okay. Um, so a ketone is just an R group. So
Oh yeah. Um, so
how
okay.
do yeah.
So, um, so yeah, in one of the PDFs, I have like a generalized, um, redox kind of pathway thing. Um, and it'll probably be something like, oh, you're probably gonna need to plug your thing in. But yeah, this over here, the
That's a
biochem
problem.
redox pathway. This is just a generalized pathway, but it's gonna always be true, so it can be helpful. So like if we are oxidizing going to the right, let's say we start off with an alkane, which is a single bonded hydrocarbon.
Mhm.
If we oxidize that, so we're essentially doing three things in oxidation, like one of three things. We're either losing bonds to hydrogens, adding oxygens, or adding bonds to oxygen.
Mhm.
So if we oxidize this alkane over here, we're going to remove hydrogens. So instead of two CH2s, we'll just have two CHs and a double bond.
Okay.
Now, when we oxidize that, we get alcohols. Now, if you get a tertiary alcohol, cannot be oxidized any further. If you have a secondary alcohol, it can be oxidized into a ketone, but not any further. And if you have a primary alcohol, it can be oxidized into an aldehyde, which can then be further oxidized into a carboxylic acid,
Mhm.
further oxidized into CO2, which is the final thing.
Mhm.
So like in the electron transport chain, the last thing that gets all of the electrons is oxygen, right? So the last thing that gets oxidized, aka loses electrons, will be CO2. So that's why in cellular respiration we, give off CO2 as a
Right.
waste product, right?
Mhm.
So that's from left to right is oxidation, and from right to left is reduction. Now you can see in green over here, I wrote so PCC is just a weak oxidizing agent compared to KMNO4.
Mhm.
So the weak one would be able to oxidize the primary alcohol into the aldehyde, but the strong one can do it all the way to the carboxylic acid.
Okay.
Now, I didn't write it. I should probably add it. Um, if you're going in the other way, if you're going the other way around, the weak reducing agent would be the sodium borohydride thing.
Which is what they said in the problem,
Yeah.
right?
So that can't reduce esters.
Everything. Okay, Esther.
But if it's lithium aluminum hydride, it's a strong reducing agent, and that can reduce esters as well. Okay.
Which of these is an ester? Like in
Oh
this.
yeah, I didn't draw it for this.
Okay.
Yeah.
Okay. All right, sounds good. There's nothing. Okay.
Mhm.
Um,
Yep.
so
So,
because,
uh-huh.
but I thought NaBH4 cannot reduce esters. Isn't a ketone? Oh, so the ketone is the last step that it can reduce because ketone is like the oxidized, when ketone gets oxidized, it turns, wait, yeah. If a ketone gets oxidized, it turns into an ester.
So the ketone can't be oxidized any further. Um,
But
mhm,
isn't the difference between a ketone and an ester is like the R group versus an OR?
mhm.
So wouldn't the oxidation be where the oxygen comes in from? Or are they just completely unrelated, just the way that they form?
Oh yeah. So yeah, in that document or that PDF that we just saw, the ketone can't be oxidized any further, right?
Mhm.
And a secondary alcohol could be oxidized into the ketone, but can't be oxidized further. Um, but it can be reduced. It could be reduced, which would mean it'll go back to turn into an alcohol. Um, now, yeah. Now the thing is with the lithium aluminum hydride compared to the sodium borohydride, like lithium one is super strong and can basically reduce anything almost. I mean, so I guess think about those carboxylic acid derivatives and um the stable ones like amides,
Mhm.
esters are the second most stable. those things are so stable that they cannot be reduced by a weak reducing agent like sodium borohydride, but can be reduced by lithium aluminum hydride, which can
Stronger.
reduce, yeah, that can reduce your
Oh,
esters, amides. Um,
you just said lithium, so I thought of lithium battery.
oh yeah, yeah. Like your lithium ion are a lot of them are in your anode portion
Batteries and stuff.
right now.
My what?
In the anode part of your computer battery.
Computer charger. The max lasts pretty long. Like we could be on a Zoom until like 7, 8, and it would still
Mm-hmm.
be going
Mm-hmm.
at 20%.
Yeah.
It's
So
almost like, do you
yep.
remember when we talked about when there was like, I can't remember what it was called, when there was like a gap in between and then it was like it couldn't pass it. Like, there was like one
Capacitor.
was open, one was closed, or if the other one. So I guess it's like until it reaches a certain amount, it like like the battery goes down quick, and then at the end it like conserves battery more.
I see. So like yeah, if you have like let's say 15% or 10% or less, it'll conserve battery life by
Uh-huh.
maybe lowering brightness or push
Energy, but yeah.
notifications or things like that.
I'm just trying to think of like that circuit. Like, do you remember earlier on in this we were doing a problem that was like, well, we talked about a lot of stuff physics related.
You're talking about like this or
Isn't that just like a regular battery cycle? It was like something where there was like um annotate is literally gonna be the definition. There was stuff where it's like if one was open and one was closed, I don't know how to draw it, or like if both were closed or were open, it's one thing, but if one was open, one was closed or
oh, you're talking
closed
about
or
maybe resonance? Sorry, not I know resonance isn't everything, but like harmonic resonance,
maybe.
like open, open, close,
Mhm.
closed,
Yeah.
and then open, close, closed, open. Um,
Because wasn't that like a gate? Like something had to happen for it to be able to pass through?
I think I'm not. I'm trying to think
I
of
might be mixing up something. I need to review and make sure.
it. Yeah, I don't
Okay.
remember, but okay. You can know that um that okay. Maybe I will send you just
For this problem.
um. Oh no, just yeah, yeah.
Physics.
So
Oh,
I'm gonna just put this
I'm gonna move over to
in
my
the
couch.
chat, but it's just the stuff that um, sodium borohydride can reduce. They can
Okay.
reduce aldehydes, ketones,
And is
acetyl.
this like something that like this specific is high yield, like sodium borohydride versus a lithium borohydride?
Mm-hmm.
Okay.
Yeah, yeah. You don't need to know like the mechanisms for this stuff, but you just need to know like what. Yeah, so like the sodium one can reduce aldehydes, ketones, acyl chlorides, thiol esters. That's just like an ester with a sulfur instead of an oxygen. Imines, but not esters, amides, and carboxylic acids, but the lithium aluminum hydride can reduce the esters and amides and carboxylic acids. So that could just be a
Okay.
like a memory thing, content thing.
Do you think this is a mile down flashcard, or should I make it one?
Pro Probably. Um,
Okay.
but yeah.
Okay. Sounds good. All right, so leave that open and go back to. All right.
All right. So
Condensation would like add H2O back.
so So yeah, in general, condensation would be like dehydration synthesis, but aldol condensation is its own
What?
thing
I've
that's
never
kind
heard
of
of
annoying, um, in all honesty. But yeah, we have to know it. So let's think about, I guess, just how. So what happens with an aldol condensation reaction is going to be different from what we typically see with, with reactions, I guess, about like nucleophilic attack and things like that. Um, so, oh, they're saying acidic conditions now. Okay. So, let's see. So, okay. So first of all, let's think about the word aldol indicates
like
presence of,
outside.
yep, and the OL would be,
You said this. This was a
you can just think
functional
about
group.
alcohol ends in
Yeah.
OL. So alcohols end in OL. So if it ends in OL, it'll be an alcohol.
Okay.
And if it's an alcohol, it means it just has a hydroxyl group.
Yeah.
So, all right. So the
Where's the hydroxyl here?
oh yeah. So the aldol that you're gonna end up getting is going to be something like a aldehyde and a OH group.
Mm-hmm.
So that's the aldol combination of the aldehyde and the OH group. Um, but typically you'll see like the OH group leave and a double bond forming, and that's typically what you'll see for aldol stuff, aldol condensation. Um, but yeah, like for instance, okay, so like for instance, if we had an acid, we can protonate the OH group to be like this, OH2 positive, and then the electron can leave with it, or rather, sorry, this can leave because it's just water, and the electrons can go and make a double bond there, and that would be your ultimate uh, end product.
Okay.
Yeah.
Sounds good.
Mm-hmm.
But that's just for a general one. So they're telling me that these are the two molecules to do.
Mm-hmm.
So that's the carbon, the double bond, hydrogen. I guess it's all there, right?
Yep. So if
On
we
what
look
I
at
picked.
these choices here, so B shouldn't be it because we want to have like just one.
CH3 in the middle, right? And also the
Yeah.
OH is, yeah.
Hmm.
Oh, sorry, I'm looking at C. But yeah, the O's, that's not necessary. We got rid of the oxygen. Um,
Yeah. So this would be like what the aldol looks like, but when you do that last condensation step, it leaves and you just get a double bond there instead.
yeah, okay. That makes sense.
Mhm.
Because I think I literally just combined them.
Mhm.
Yeah. But then I'm not considering the aldol condensation reaction. Okay, I understand.
Mhm. All right. Now these are like this is probably like one of the only subjects that or topics that I really hate. Uh HNMR never was really good at that, but let's do it. So, okay. So it's basically it's a way for you to identify unique hydrogens. And like ultimately it can tell you like the exact like exactly what a molecule looks like.
Mm-hmm.
And when you do that, you consider uh the non-equivalent hydrogen neighbors. So for instance, here, this is just, CH3 with
Yep.
these three hydrogens, and its
Mhm.
neighbor has
2,
two hydrogens. So if we looked at
5.
this over here, like if we're looking at just this carbon here,
You have 3.
we have, yeah, we have three on that,
And then the
but we go by the number of neighbors. So the neighbors is going to be
2.
2, and that'll be like the n number, and then n plus 1 will be the number of subpeaks. So that'll be 3 subpeaks. So that'll look like a triplet,
Mm-hmm.
right? Now they're asking about,
Methoxy
yep,
and methyl we said was what's the difference between methanol and methyl?
a methyl on its own is just a CH3, like a methyl added to the group.
Oh, okay. All right, sounds good.
Yep.
So the methoxy is just this, and so we have to take into consideration this carbon,
Uh, so if they're saying this, right, then this carbon, right?
but I thought you said the neighbor.
Oh yeah. So that's the thing here. This carbon's neighbor is oxygen, which doesn't have any hydrogens. So there is no neighboring hydrogens
So
here.
is that why it's a singlet?
Yeah, because n is 0, and then n plus 1 is 1, and that'll give you your singlet.
Got it. So
Mhm.
didn't we count the number of hydrogens though, and there's 4 hydrogens?
Um, so you're saying,
It's the H3 and then this one. Or
yeah,
the second
so
one.
so these three hydrogens, their neighbor oxygen has no hydrogens. So you go
Doesn't
by the
hydrogen
neighbor.
usually have 2?
What's up?
Doesn't hydrogen want to have 2, like, to be stable?
Um,
Like, 2. What am I thinking of? I don't know. Kind of
maybe you're
tough.
thinking of oxygen needing 2 valence electrons. I'm sorry, having 6 valence electrons and needing 2 to be stable.
Possibly, yes.
Hmm.
I'm thinking of formal charge, number of bonds, number of lone pairs. So if
Oh yeah.
oxygen has 2 bonds, it wants to have 2 lone pairs.
So
That's different.
so uh like yeah, like H2O, right?
Mm-hmm.
So oxygen has 6 valence electrons, and it just needs 2 more to complete its octet.
Okay.
And it can gain that by making bonds,
Mm-hmm.
right? So this oxygen has 2 bonds, so it has 2 electrons added, so it completes its octet, so it's able to be stable in by making 2 bonds.
Mm-hmm. Okay.
That's why we usually see oxygen making like 2 bonds or like a double bond and stuff, right?
Mm-hmm.
So yeah, this one would be, it has
This
this, yeah, this group has no, yeah. And then here, I guess, are certain examples. So like, um,
the ones that they're giving are
mhm,
that makes sense.
yeah.
Cool.
Mhm. All right. So this goes back to the stuff we talked about regarding fluorescence.
How neon
What's up? Maybe you're
weren't
thinking like
the
neon lighting or something.
well, yeah, but I'm also thinking like aren't these the most fluorescent?
No, so fluorescence, we talked about this before. It's when you have a molecule that absorbs a photon and causes that electron to be excited.
Mhm.
But it can go relax to a lower position because of its resonance stabilization. So, yeah.
Okay.
Like, remember when we talked about like the three scenarios for photons? Like, scenario one is when you just have energy of a photon absorbed is equal to the energy of the photon emitted.
Yes.
And then scenario two, fluorescence, energy of a photon absorbed
Is
is
less
more
is more than.
than the energy of the photon emitted. And then
Mhm.
the last scenario is with the work function. If energy of a photon exceeds that work function, it will cause the electron not just to be excited, but to be ejected, actually leaving the atom.
Okay.
So, like, if you look at the so basically, um, you know, n is equal to 1, n is equal to 2, n is equal to 3. So if an electron, if a photon that has enough energy to excite an electron from n is equal to 1 to n is equal to 3, right? Typically, it will go back down to 1 and emit a photon of that same energy, right? However, if the molecule contains a lot of conjugation, meaning like double bond, single bond, double bond,
Right, right.
aka can involve itself in resonance, it stabilizes it. So it's like let's say like I don't know. I don't know, I'm thinking of this example. Let's say that somehow someone's like, okay, this is your kid, whatever, and it's like a lot, it's not easy to take care of that kid or whatever, and it makes you very stressed. And if you like were to, this is a bad example, but if you get an electron, you get excited, and if you're excited, you're inherently less stable. So you want to give that give the photon away to take your electron down to a more stable ground state. But let's say you do that, and when you're up here and you're not stable, you like do some stress, you like meditate, you do some breathing exercises, and you can lower the energy of that electron without having to emit a photon, right? So then eventually, when you go from N2 to N1, you will emit a photon, but it'll be of a lower energy than that photon that you absorbed. And so this is, oh,
It's
and
like
the
kind of like
Mohs questions.
kinematics when you're lowering like an activation energy.
Um, you're thinking of kinetics.
Kinetics, yeah.
So that's more so along the lines of if you add a catalyst, it can enhance uh the orientation of the two reactants or however many reactants to be like able to form a bond or react with one another. But this is like, so I made like those Mohs questions for you that all have to do with fluorescence because
Mhm.
that's a huge thing. And so the idea behind that is if you have a molecule that has a lot of conjugation, it's going to be able to undergo fluorescence. And so if you look up like the structure of a pigment, right? Like melanin or chlorophyll or something like that, right? So yeah, we can see tons and tons of conjugation,
Mhm.
right? So so that's why when UV light hits, like like my skin, I have some melanin, so it can absorb that UV radiation and emit it as lower energy light. So that's why it's also called UV vis. So it can absorb the UV radiation that's high energy and dangerous and emit it as visible light, which is fine. And so uh So that's why if you don't have that
That
much,
what like a sunburn is, the visible light.
so yeah, the sunburn is going to be no, not from the so like if so like I can't get sunburned because of the melanin, but if you don't have melanin, you can get sunburned because it means that the UV radiation is directly hitting your skin cells and it causes those thymine dimers in the uh
Mhm.
in the DNA that leads to like melanoma and all that stuff. So
Okay.
that's why like you should wear sunblock, but and sunblock would be composed of something that can absorb that UV radiation, but like melanin does that as well. So it's always going to look like something with like this, with tons of conjugation.
Okay.
Mm-hmm. And so, yeah, so
I'm
absorbance
looking
on
at
the,
these. The one with the most conjugation is obviously B.
mm-hmm. Yeah, yeah. If this
So,
looked like that, it probably still won't have as much as B, but it would have conjugation then, right?
so like looking at these like other
Mhm.
answers, let's say B isn't here. Would A be the next one because of the shape?
Um,
Don't like like the rings, aromatic rings, like they're usually like I know that like they're resonance stabilized if
so
it's
this one wouldn't be. You would
this
need,
one wouldn't be because it's every other one as
yeah,
a
yeah, you need double bond, single bond, double bond. Um, so yeah, and then this is a type of so like now we're in the region of like spectroscopy. So there's like HNMR, which we did, the UV vis, right? IR, um, mass spec.
Mhm.
So UV vis, the purpose of it is to check for triple bonds, double bonds, conjugation, essentially.
Mhm.
Mhm.
Got it. Okay. I get why it's B. I just wanted to like see like based off of like C
Yeah. So if
and
if this wasn't here and this was just here and here, aka benzene, it would be better.
then B,
Oh no, no,
just in general.
better
Okay.
than what
But
A
then
is.
this one is still harder to break apart than the oxygen one, right?
So you said this one?
C, like between C and D, C would be no, I'm sorry, D would be harder to break down.
Oh, in the form that I drew it?
Well, no, even just in general, the way that it is regularly between C and N, the double bond, oxygen, isn't it that a worse leaving group than carbon? Like carbon's,
Oh, so we're not doing anything with lead. We're not like really changing, doing a chemical reaction.
I'm saying
But
like in an
uh-huh.
in a problem that's like harder and B isn't like such a clear winner. Like how
Yep.
do I look at them and like A, C, and D are kind of all like eh.
I would
Like
say
A
that
has two
C
double bonds.
C would be the second best because if you think about it, CN is a triple bond there. And so UV, like Biz, like in addition to all that conjugation stuff that I talked about, like double bond, single bond, double bond, it also detects triple bonds.
How is C on a triple bond?
So if you go back to the Lewis structures, 1, 2, 3, 4, C carbon has four valence electrons, right? Nitrogen has 1, 2, 3, 4, 5 valence electrons, right?
Mhm.
So we would want the carbon to make four bonds, so it makes one there. And then these three, and three of these from nitrogen. So I'm just going to move this one and this one. Sorry, I'm going to move. Damn it. So I'm going to just put like three here and then two here as the lone pair. And so this, and that would bind, right? And that way you have carbon's octet satisfied and nitrogen uh, also satisfied with 1, 2, 3, 4, 5, right? and then 6, 7, 8 as it makes the bonds. So, and HCN is hydrogen cyanide. This is all cyanide, which you shouldn't take because it's not.
Poisoning, cyanide poisoning. I remember that.
So, yeah.
Okay.
So if you're ever like confused about like what a like CN would look like, just go back to like the Lewis structures where you draw the valence electrons and then
Okay.
go from there. Yeah.
Sounds good. Right.
Oh yeah, and then this stuff. So yeah, this one I would just like
Is
kind of
IR spectrum not like when they say,
Mhm.
or no, this is chem, not physics, right?
Like it's like everything, it's
Yeah.
all up together, but sure, yeah. I would say it's probably like yeah, it's like organic chem,
Okay.
but it still involves like physical sciences. So, but yeah, so for the IR spectrum, like there's like the region, there's like a double bond region like there. So we're gonna have your fingerprint region all the way on the right, followed by a double bond region, followed by a triple bond region, and then lastly a single bond region. So typically speaking, the ones that I would remember are like carbonyl group, that's like 1750. That's this guy over here. And it's a sharp peak. Okay. And then like cyanide and whatever, triple bonds will be in this range. Um, but then the other one that comes up the most is the alcohol group, the OH group. And that's going to be in the single bond region, of course, but it's going to be like broad. It's going to be a broad peak. So they didn't really, oh, I guess they mean that. But yeah, that'll be like, you know, uh, at this range over here.
So the narrow peak are these ones?
Mm-hmm.
This one's okay, understood. So what was here? Was it carbonyl carbons?
Oh
And this
yeah.
is hydroxyl?
Mm-hmm.
Okay, makes sense. Let
Yep.
me take a screenshot quickly. Okay. Go away. Thanks. So ethyl acetate would be, what am I calculating here? Is it the problem that was asking for like the neighbor n+1 thing?
So okay, I just put
Or
something in the I'm gonna put two things in the chat. So oh hold on. Yeah, that's because it's a transparent background, but here. I just sent another one. But yeah, that one with the yeah, so here you have your fingerprint region, double bond region in yellow, triple bond region, um, single bond, stretch. That so like since it's able to stretch more a single bond, you're gonna see like not you're gonna see more broad stuff there, broad peaks. And then this up here, the orange or yellow picture, those are like the most common ones that you'll see. So I that would just be like pretty much like a memorization thing
okay,
for the most
sounds good.
part. But oh great, it's another H&R problem. So ethyl acetate. So all right, so I guess this way we get a better kind of example to work with. So like let's just go with
Ethyl
Mhm.
is, let's test how well I remembered. OH.
Mhm.
And then acetate is that like acetyl.
Oh yeah. So is this you're drawing ethanol here?
Yeah,
Mhm.
is that right?
It's right for ethanol, yep.
Yeah, I was doing ethanol. For acetate, is it like ATE is when O is reduced or ONE is reduced?
So ATE would be like the deprotonated form of something like, ic acid or whatever. But so basically what we're having here is, so if we know that acetic acid is this over here,
Yes.
when it loses that proton and it's negative, it will then be called just acetate. So
So,
I'll do
okay,
it like
yeah.
this. So this is acetic acid, and when it gets
When it
deprotonated,
loses, it becomes acetate. So,
exactly. Yep. So we're really just taking that acetate and we're adding an ethyl group to it, which is,
what
two
I
two
drew.
carbons. So this is ethanol, right? Ethanol, but
Uh,
but ethane would just be, would just be this, like,
ethyl, right?
oh yeah, so ethane is what I drew, but now if we add that to the acetate molecule, it would be considered like an ethyl group.
Okay.
So acetate here. Now let's add the ethyl, the ethane to it, which will be an ethyl group. So then that would be like that. So we have our acetate part here and the ethyl
CH3.
part here. Yeah.
Because the NMR thing was when we went off of neighbors, right?
Mm-hmm.
Better to have them.
Mm-hmm.
This is also CH3.
Mm-hmm. Yeah.
And then this one has 1, 2,
Mm-hmm.
oxygen, none. This 2, 2.
What's that two for?
Never mind. I didn't think about it correctly. It's 3 and 1, so there's only one carbon here. Hydrogen.
Well, so how many bonds can carbon make?
I keep looking at it from the wrong angle because it's not like together. Okay, I understand. So no, this one doesn't have any.
Mm-hmm. Yeah, it already has the, like, all right, maybe if I drew it like that.
Right, so there is the carbon here.
Yep.
Okay, I understand. So
Mm-hmm.
then that's what they're drawing out over here, right? Like with all that stuff. So how many peaks?
Mm-hmm.
What are the peaks? Like the same as the last problem with the like with the curves,
So that was for IR.
broad and narrow peaks.
So that was for IR.
Uh-huh.
So this is back to HNMR, where we
Yeah,
look
but
at,
HNMR was counting the neighbor, right? It was n+1.
yeah.
But if the whole thing is ethyl acetate,
Mm-hmm.
I'm not sure I understand what the peaks are.
Oh yeah. That can be a little confusing. So like, so so N will be the number of those neighboring non-equivalent hydrogens. N+1 is going to be the number of sub-peaks. So the N really represents the number of peaks. So that could be a little ambiguous there. But
Okay, I understand.
mhm.
So anything that has hydrogens is a peak?
Oh, so like, okay, if we look at this molecule here,
Yeah.
let's just go at it, like one, I guess, carbon at a time. So like the leftmost carbon
Then move down.
has the three green hydrogens, right?
Yeah.
But they don't have any neighboring hydrogen, right?
No.
Correct. And so that means, so n is the number of neighboring hydrogens, that's 0.
It's
So
a
it's going to
singlet.
be, yep, it'll be a singlet, and that's why we have that there.
So why is it the highest when it's a singlet? Because there's no like energy coming from a neighbor.
Um, I guess that part isn't really that important.
Like why would it be the highest one rather than the lowest one if it's only one? That's my question.
My guess would be that if it's a singlet, it can, since I guess in HNMR, or what you're doing is it's basically the same thing as an MRI. You shoot radio waves at it, you get it to flip and
Smaller it is, the more
flip it
dangerous the
back.
waves.
Um, oh no, just like, well, radio waves are fine with us,
Okay.
right? But
Yes.
but basically it'll cause like molecule to flip, and then it'll reverse that uh field to make it flip in the other direction, giving off a signal. So if it's just a singlet, it's all of that radio, like all of that absorption and stuff in one thing. My guess would be if you took the length, so this is what, 300, and then this is 600. If I took 300 plus 300, right, to get 600, I would get 1200 up here. So if you're splitting it, it makes sense that it would be smaller because you're splitting it into more than one signal,
Okay.
right?
Makes
You see
sense.
that?
Yeah. Yes. So then the second one would be H, which does have a neighbor.
Mm-hmm.
Wait, no, this one, because it's the neighbor plus one, so this is 3 versus this is n plus 4.
Oh, so
This one's a
this carbon here with the red hydrogens
the
has,
neighbor for the red is 3 plus 1, n is 3.
yeah,
And for blue, it's 2 plus 1, so 3.
yep.
So 4 ends up having a small, like, sorry, blue has a smaller neighbor than red does. So red is lower than blue.
Yeah, yeah. Like I wouldn't worry again too much about the heights, right?
But then peak wise, yes, there's 3 heights, not 2. So I
Yeah.
understand.
So now when they say peaks, that could be a little confusing. So, because what they mean, like they don't mean sub peaks. So like it's just, even though this has 4 sub peaks, 3 sub peaks, 1 sub peak, peaks just mean that's 1, that's 2, that's 3.
Okay, sounds good. I just really want to finish these last 3 ones.
Mm-hmm. Yep, we're almost done.
Okay. Um, I don't know why
Oh,
it's
so yeah, they don't tell us here, which is kind of annoying, but this uses silica as its stationary phase, which is polar.
Mhm.
And you know how, like, so chromatography in general, right? It's a separation technique that separates things based on
Mass,
their,
charge, some property,
yeah,
size.
so it's based on their affinities for the stationary phase,
Oh, okay.
right? So if something has a higher affinity for the stationary phase, it'll be the last to elute out. So
So if it's polar, then acid would be drawn towards it. So based off of affinity, it would be hold on to it last.
Correct. Yeah.
So at the
Hold on
lens,
to it first and then blast to leave. So
okay,
seems like you had the right, you were able to find the pattern. It's just that they didn't tell us that it's polar, so it's
okay,
just the other way around. But your
okay.
logic was good.
Right.
All right.
I can't remember how I did it. I remember I counted something
Mhm.
in like chromatography. The retention factor of the compound in lane 3 is approximately lane 3. It's here.
Mhm.
Oh, 8.8. Why is it half? Because this goes up to 16.
Mhm.
Got it. Okay, that's simple.
Mhm.
Um, techniques is used to separate two compounds.
Mm.
Yeah.
So.
I'm just thinking like distilled water is that you use
Mhm.
uh autoclave to sterilize like medical tools. So
Uh-huh.
vacuum distillation, I guess, is the answer because like when you seal the autoclave, it like creates like a vacuum. And you
Yeah.
can put
So.
it into distilled water. Okay, I understand.
Uh. Wait. So I don't know what you mean about that.
I'm like using like outside knowledge to try to answer because like looking at this problem, I have like quite literally no idea, but I'm thinking like in a medical office, like to clean tools, like you can't just like run them under like a normal sterilizer, it's not enough. So like distilled water, I know is what gets used for.
Yeah, but we're trying to figure out what type of distillation we do, right?
Yeah, and then I thought like an autoclave, the tool that you put it in. I'm just gonna run you through my logic and then you'll explain the problem to me. Autoclave, you have to like push down like a whole bunch of levers, like create like a serious like vacuum seal. Like it literally won't even turn on if you don't have it sealed properly in order for the sterilization to go through.
Yeah. But
Yeah,
that's so we want to separate using distilled water
from distilled.
from the distillation process, right? So, for instance, so this is another type of separation technique. All this stuff falls under separation technique. Like filtration is a separation technique, right? So every separation technique will take advantage of certain property that's different between the things that you're trying to separate, right? So like if you're using chromatography, what's different between the things you're trying to separate? Their affinities for the stationary phase, right?
Yes.
Okay. Now, for distillation, what would be the property that you take advantage of to separate things by distillation?
The opposite, like the lack of affinity.
So, it'll be the boiling point.
Okay. All right. Sorry.
So, if you have some thing here and you have some fire underneath, and then we have, a mixture here of like two different things, right? Uh, whichever thing, so let's say A, B, right? A has a melting point of 8, B has a melting point of 4. Doesn't matter the units, I'm just putting it out there. So whichever has, sorry, boiling point. So which would boil first?
The one with the lower boiling point?
Yep. So if this is A plus B, B would boil and come up here, and then this is some, cooling condensation region where we condense it back to water or back into the liquid form, and then we can collect it in this little bucket. Are you there?
Mm-hmm.
So that means we can then have B here, right?
Yes.
What do you do?
Sorry, no, my
Oh, I thought you were doing something.
I don't know what. It like showed me a notification that I had low battery, so I closed it.
Oh, okay. Yeah, so we take advantage of separating them based on their different boiling points, right?
Yes.
Okay. Now, if you had something with a really high boiling point, right, like 150 C,
Mhm.
right? Um, that's going to be difficult to heat up to that high temperature.
Right.
So what you do is you create a vacuum,
Mhm.
like sucking,
Not being exposed to like a cooling agent of any sort.
oh, in the condensation chamber. Yeah, that would be this would be some type of cooling thing to cool it back
Still be there.
from the what's up?
It would still stay there.
Oh, because like yeah, because you want to evaporate or boil that compound B or whatever, but to to collect it, right? You're gonna want to condense it back,
Got it.
right? Okay. Now, if you
Gravity filtration.
what's up?
What is gravity filtration?
So it's basically like probably the simplest one. Just imagine like a little mechanical, like a filter with little holes in it, and you put something in it, and it separates like the solid from the liquid.
A water filter? Like
Um,
the
no, it'll typically be used for like filtering a solid from a liquid.
okay, all right. So like when you're
Oh,
cooking and you put it in like the coriander,
yeah.
whatever.
Uh, yep, something like
Okay.
that, or like a regular coffee
All
filter,
right, sounds good.
that kind of thing. But
Mhm.
okay. Now, vacuum distillation versus simple distillation. Now, boiling point, if you think about it, right, it's really when the vapor pressure is equal to the atmospheric pressure.
Mhm.
Okay. Now, if you reduce the vapor pressure, right, you're
Yeah.
going to be, or sorry, yeah, if you basically clear that area, it's gonna lower that boiling point if you create a vacuum in that in the distillation process, right? So that is what we can do to boil something, uh, but to reduce the boiling point of something that has a really high boiling point.
Sounds good. That makes
So
sense.
so tell me what distillation does.
So distillation separates like something with a lower boiling point from the rest of the compound, so that's able to
Mhm.
evaporate upwards. And then the distance between simple and vacuum distillation is that vacuum separates it from like any other like things that could slow down the heating process, especially because it's super difficult to boil something to such a high like boiling point as like 150
Yeah,
Celsius.
so everything you said was perfect, but one thing, so the vacuum part just lowers the boiling point.
Okay. Oh, wait, like actually, okay.
Yep.
I thought that there was like nothing that could lower or like change a boiling point of like a liquid.
Oh yeah, I
Like
mean like have you
water
ever been
boils
to
at
like
100.
have you ever been to like a high altitude like mountain or something? So there's less air pressure there. There's less atmospheric pressure, right? Because the air gets thinner.
Hmm.
So the boiling point at those high temperatures, right, will be a lot lower.
Really
Yep.
interesting.
I
Wow.
remember when I was a kid, there's some food that I would add water to, like ramen or whatever. And it's like if you're at high altitudes, you're gonna have to. It'll take longer to boil or whatever. I mean, take longer to make the food because it'll boil so much faster. But
Mm.
that's just because boiling is when the vapor pressure is equal to the atmospheric pressure.
Very cool.
So at high altitudes, lower atmospheric pressure, so lower boiling point. Then one more. All right.
Yes, I
Oh,
mean
this
this
is
one.
this is annoying because they're calling it gel filtration, which is like never what it's called. But apparently it's size exclusion, which just means that the smaller things take longer.
I was
Uh,
thinking like gel electrophoresis.
yeah,
Yeah.
I don't know
All
why
right.
I'm calling it that.
Cool.
But yeah, there you go. So you've seen everything of the topics that were the most
Yeah.
foreign to you. So you have seen all the physics stuff, you've seen all the organic chem stuff, and yeah, that's the stuff that to work on. So now you've seen it all. So yeah, I would say tomorrow, like, would you be up for taking a practice test tomorrow?
Yeah, I think so. I think either tomorrow or Sunday. What are we meeting this weekend? Do we have a lesson? I like was looking through my calendar. I don't know if I
Oh
see
yeah,
it.
not for this weekend. I'm actually going home to see family,
Okay.
but uh but
So,
it seems like you have an hour scheduled with me on Monday
oh,
and an
I see.
hour on Tuesday and an hour on Wednesday.
I think I scheduled through the 30th, so I have to go and add more.
Yeah.
Okay. All right.
And yeah, if you can do like the 2 hour or 90-minute sessions, I think that would be good because we want to like now we're entering the phase where we're doing the full length. So, you know,
Going on
do
for way more
you'll do
time.
your full length and then do you
Blind
remember
review on
blind
Sunday.
review? Yeah. And then
Okay.
the regular review. And then when we meet, we're gonna go over all of that stuff from the full length.
Mhm.
And you're gonna learn, and then you'll take the next full length,
Okay.
next weekend, and then you'll go over that. So that's
Um,
gonna be like the workflow now. So which full length?
which one do you want me to take? Another blueprint one? I think we
No,
said
no,
blue.
no. So now,
Oh,
we only
AMC.
have time for like the AMC ones now. So the AMC, it'll be one that you haven't done. So which ones did you do? Like, was it
I think I can do AMC too. I
okay?
haven't done that
Which
one.
which ones have you done?
I did content diagnostic and I did AMC one this time around. I don't
I mean,
remember.
like total, in total.
I don't think I did two before either.
So yeah.
Just to be safe, I can start from the third one if you.
Okay. Uh, so which ones? Sorry, which ones did you do?
I did content. There's like one that's like unscored
So the you're saying
and
the
AMC one.
unscored AMC one,
There's unscored and then there's AMC one. I've done both of those.
AMC full length one. Okay,
Yes.
and no, you haven't done any of the other ones, right?
I can't remember if I did two. I don't think so, but that's what I'm saying. If you want to play it safe, I can start from number three.
Oh, like when you log in, it'll show
Okay, yeah.
you.
All right, sounds
So
good.
yeah, so just yeah, so yeah, so tell me which
You
one you
want that I
take.
haven't done before.
Yeah, exactly.
Okay.
And um, yeah, good luck.
Okay, thank
All
you.
right, all
Bye,
right.
Shane.
I'll
Have a
see
good
you.
weekend.
Yeah, you too. All right,
Bye.
take care.